a new tradition in the department. Every Monday at noon, we're having lunch with any students that want to show up, with faculty and the students, in the W&B place in the new student center. Brewster?
Brewster, yeah.
W&B. And tomorrow at lunchtime, there's a capstone meeting for those of you who are involved in research, and also going on all day, and we probably should subsidize this since we get pizza for the capstone lunches. There's a pizza fundraiser from Mountain Mike's.
No.
That's going on, and we have flyers up here for that. 11 a.m. to 9 p.m. They get 20%, the Society of Physics students gets 20% of whatever you buy from Mountain Mike's Pizza, the one on Southwest in Snyder. So go eat pizza tomorrow, and delivery, takeout, or dine in. It's all good. Also, we just sent out the announcement to students who are interested in doing research in the summer for our 2 research fellowships, the McQuillan Award and the Newkirk Award. The applications are due to me on March 14th by 5 o'clock. So if you'd like to be paid to do research this summer, please find somebody to work with, talk to them about what you'd like to do, write it up, and send it to me. And we give out 2 of these awards. Next week's talk is, this is the beginning of Women's History Month. We're in March, yay! Women's History Month was started here at Sonoma State, and so to honor that, we are featuring all women physics speakers for the month of March. And next week, our speaker is one of our physics graduates, Melissa Crane-Geisinger. She graduated from Sonoma State with a degree in physics, a BA degree, in 2007. And she is now an entrepreneur running a web design and photography company called New Skin Media. And her talk is going to be Physics Springboard from BA to Entrepreneur. And she also runs various meetup groups about web design and things like that, so she's really got a lot of interesting things going. And if any of you have ever looked at my own personal web page or my ranch pages, she designed those back when she was a student, and I haven't ever changed them because I've liked them so much. So, very talented individual. So come hear her next week. This week I'm very excited to be able to introduce to you Dr. Jocelyn Read. Jocelyn got her bachelor's degree, BS, in physics and math. She's Canadian, so this was at the University of British Columbia in Vancouver. She then went on and got a PhD at the University of Wisconsin in Milwaukee. And her thesis was Neutron Stars and Compact Binaries from Equation of State to Gravitational Radiation. She did a couple different postdocs, one at the University of Mississippi and another one at the prestigious Albert Einstein Institute in Potsdam, Germany, where our very own Ben Owen actually did his postdoc as well. So I'm actually familiar with that place. She's now an assistant professor at Cal State University Fullerton, where they started the Center for Gravitational Wave Physics. And she's going to talk to us today about gravitational wave physics, listening to the Symphony of Space-Time. Please join me in welcoming her.
Am I supposed to have a microphone?
No.
Okay, cool.
No, just use your teacher voice and it should all be fine, and that is the microphone for YouTube.
Ah, I see. Great. Thank you. Okay, thank you everybody for coming today, and thank you very much for inviting me to speak here. I'm looking forward to this. So I'm going to be talking about a new way we are developing to learn about the universe. Most of the time when you take an astronomy class or go to an astronomy lecture, you hear about things that you can see. You see these beautiful pictures of galaxies and nebula. And what we're doing now is trying to hear the universe too. And since there's no air in the universe, the medium that carries the sound of space-time, or the sound of the universe to us, is space-time itself. So that's what I'm going to be talking about today. So very brief outline. I want to start by saying a little bit about what gravitational waves are. These are the ripples in space-time that we hope to hear. I'll talk a little bit about neutron stars and dense matter, which is the type of gravitational wave source that I study in particular. And the sort of finale of this is how we can use the gravitational waves to learn about neutron star astrophysics. So we come back to the more traditional areas of focus for astrophysics, but now we have a new technique to try and learn about these things. So I'm actually probably going to spend at least half the time on this first section, because I want to sort of go back and start by introducing what gravitational waves are, assuming that you know very little about them. And so the 0th order step for that is to go back to our ideas of gravity and relativity that set the stage for the theory where gravitational waves emerge. So first off, the very origins of our theories of gravity kind of come from Isaac Newton's realization that the same reason that things fall to the ground on Earth is the reason why the moon is orbiting us. So the moon is always falling towards us, it's just moving fast enough that it keeps missing. The process that has things fall to Earth and the moon fall around the Earth are the same force of gravity. So that's sort of step one. And then this force of gravity in the Newtonian theory occurs between any massive objects. You and me, the Earth and you and a galaxy billions of light years away, all feel gravitational forces. So that's this foundational description of things that describe how matter in our universe interacts with itself. And then the other step towards the foundation of space-time is this idea of relativity. So just what we call special relativity, which is starting to try and play with how observers traveling at different speeds perceive things. And the two key ideas from this theory are that nothing can travel faster than light. No information can travel faster than light. And that space and time are not really these distinct things that we perceive them as. So what I call space and what I call time are dependent on how I am moving. And in our theory, it's better to join these two together into something called space-time, because we can't isolate them from each other in a way that everyone's going to agree with. So these are sort of the foundational concepts that come into the theory where we talk about gravitational waves. And I'm going to talk about general relativity, but only in one slide and 3 bullet points. So I think there's just the bare bones framework of this idea. Okay. So the starting point is that gravity, this force that we feel, things falling or orbiting, is just a property not of some sort of force that acts at a distance, but a curvature of the space and time object that we talked about earlier. So gravity is actually a geometric property, that we have space-time curved by the presence of mass or energy, and then we have 3 kinds of examples of what this can do. Okay, so the first thing is that something that's freely falling, something that doesn't have some rigid structure supporting it or some other forces applying to it, it will just follow the straightest possible path. And this is actually all you need to get an orbit. The moon is following the straightest possible path through space-time, and because the Earth is curved space-time, the moon ends up looping around the Earth as it travels. Nearby paths can diverge, so the way that space-time curves means that 2 things that start out traveling side by side can be curved apart from each other. And that's why we have the 2 sides of the Earth being stretched apart with tides. So two different points or 2 different objects traveling can diverge from each other because they're moving through a curved space. And the final thing is that changes in the space-time will propagate at the speed of light. So you don't feel the force of the Earth directly. You are moving through the curvature that the Earth has induced in space-time. So if we change the way that the Earth is producing curvature, that change doesn't hit you immediately. It takes time to propagate out through the system that you're in. And that's what gives you waves. So the foundational concept that lead to this idea that gravitation can have gravitational waves in space-time is just this idea that gravity is a space-time curvature, but those changes can't propagate instantaneously. They have to ripple out, and this is what sets the stage for setting up a wave pattern that can travel. So I'm going to spend a little more time on these two pieces here. So, well, actually, the foundational piece and then these two implications. So you may have seen these kind of embedding diagrams for how a massive object curves space-time. So if we have something like the sun, it's just a little dimple curving the space-time. But if we try and put more and more mass into a smaller area, we can get more dramatic curvatures of space-time, the most dramatic of which is a black hole, a situation where space-time has curved so dramatically that light can't even get out of it anymore. Just for fun, if this is not on the screen 0.7 inches, but if you printed this on paper, it would be less than an inch. That would be the approximate size you would need to compress all the matter in the Earth down to turn it into a black hole. So they're very dense. They have a lot of mass compressed down into a small area so that if you get close to it, you feel very strong gravitational forces. And you can see how an orbit is produced by this kind of thing. If you look at these stretchy tables, where you see that these little marbles, if you roll a marble around a flat table, it just goes in a straight line. But if it's rolling around a curved surface, they can end up looping around the point of curvature. So this would be an example of a massive object and some bodies traveling in curved paths around that central mass. Okay. So although we can have very extreme cases of curvature, these objects behave the same way things in our solar system behave when you're far enough away from them. So for example, we can see stars in the center of the Milky Way galaxy moving in orbits around a central point. And we can use the orbits and the Newtonian-style gravity to show that that central point is most likely a black hole with a mass 4 million times the mass of the sun. So when we're far away from these strong curvature areas, we get back the kind of orbits that we're familiar with from our own solar system. So the other part that I talked about was this changes in space-time propagating at the speed of light. So we have curved space-time and things moving through that. Now let's talk a little bit about what it means to have a wave. So most of the astronomy we do is with electromagnetic waves. So here we have magnetic fields and electric fields that rise and fall as they travel along a direction of motion, so that if I have, say, an antenna here, the electric field is going to move electrons up and down in the antenna and give me something that I can measure. Or if I have so there's a lot of cool stuff that you can do with electromagnetic waves. But the idea of the wave is that we have some ripple back and forth in the electric and magnetic fields that sets off a pattern that propagates in space. And we can do the same thing for a gravitational wave. So now, what we have changing is stretching and squeezing of distances between objects. So here at the front is an example of a slice of space that is alternately getting stretched and squeezed in different directions as I look at it. This is a gravitational wave, a stretching and squeezing that sets up a ripple that travels at the speed of light through space-time, propagating along in this direction, so that something that kicks up a wave back here will cause this kind of pattern of stretching and squeezing over here. So there's, in an electromagnetic wave in light, the things that are changing are the electric and magnetic fields. In a gravitational wave, the thing that's changing is the distances between space things and space-time. So this tells us what kind of system can set this up. And what you need is you need some objects that are very compact so that they're curving space-time a lot. They need to be moving around each other. And they need to be moving in a way that's going to set up one of these ripples, what turns out to be a changing quadrupole moment, which is basically something that has some separation that changes in some mass separated and changing in time. This particular system, so this would be, for example, 2 black holes or 2 neutron stars orbiting around each other. If this was very far behind the board, this is what this would cause the space-time to stretch and squeeze right in front of you, the observer. So you're going to look towards some system of distant binary objects, and you're going to see this stretching and squeezing in this particular pattern. We know of a few other things that can kick up this kind of stretching and squeezing of space. So things like supernova, where you have a big change in the movement of matter all at once. Or if you have a compact object that's spinning with a little lump on it, that sets up a little ripple around the lump. Or if you have supermassive black holes at the center of 2 galaxies merging together, all of these things will kick up gravitational waves. The ones that are kicked up by supermassive black holes are very low frequency. This is something that happens over years. The ones that I'm going to be focusing on in this talk are more the high frequency things, because that's what we're going to be trying to listen for with our detectors here on Earth. So I'm going to show you a few kinds of representations of a gravitational wave through this talk. So one thing is just to plot what the signal looks like. And to do that, I'm going to say, well, I'm going to put down a little framework on my stretching and squeezing space-time, and I'm going to compare the length in one direction to the length in the other direction as they get stretched and squeezed. And then I'm going to look at the difference between those. So sometimes L1 is going to be bigger, sometimes L2 is going to be bigger, and this is going to give me this gravitational wave pattern, which is this difference in the lengths in the 2 different directions. So here's where one side is bigger, then it's smaller, then it's bigger, then it's smaller, and we get something that looks like a regular kind of sinusoidal wave pattern. So if we had a continuous wave source, this is what we would produce. And you could actually hear this as a pure tone. So I don't actually have a pure tone. I should really add one of those to this. But for example, if this was at an audio frequency, you would just hear it as the same kind of tone you would produce on a piano or a computer speaker or something like that, just a solid note. For the binaries, though, we have something else. So when I showed you the picture of the little marbles rolling around on the elastic sheet, they fell into the center. Now, that's not a good model for our solar system, because the planets and things in our solar system don't fall in. The reason they fell in on the rubber sheet was that they were losing energy to friction. The gravitational waves are carrying away energy from the system in the same way. So the things orbiting around each other, they kick up gravitational waves. The waves carry energy away, so this system is losing energy. And that's going to change how the 2 objects are separated and how fast they're going around each other. So the change in the energy of the system is going to be decreasing. And for an orbiting system, that means they're going to fall towards each other slowly as they lose energy. So this is something that we've seen. This is what's called the Hulse-Taylor binary pulsar. It's 2 neutron stars. These were the most compact thing before you got to a black hole, orbiting each other once every 7.75 hours. And what you often see is this plot here that shows what's called the Periastron time shift. So you measure these orbiting pulsars in Doppler, and you see how often they pass a certain point in their orbit. And you find that that time shifts from what you would predict if they were in an orbit with a constant frequency. So we can actually go through the math for this just in a minute. For those of you, how many of you are familiar with the Taylor expansion? Okay, so you can do this. Okay, so we have the periastron time after some number of orbits. And we can just make this a Taylor expansion. So it's the change in time per orbit plus the second order Taylor expansion term times n squared. The time per orbit is a period, and if you take the derivative, the second time derivative, you actually get period multiplied by the rate of change of the period, just taking some derivatives there. So that means that the time after in orbits is going to be some regular ticking n times the period plus something times the number of orbits squared times this pp dot. So this would be what the periastron time would be for a constant period. It would just be a regular constant contribution. But what we have is a changing period. The gravitational waves are carrying energy away, and that changes the period over time, and that gives over time a quadratic change in the number of orbits that you see. So that's this quadratic fall off here. The black dots are the data taken by observing the system, and the solid line is the prediction of the energy loss due to gravitational waves. So we have this very solid evidence that gravitational waves are affecting things in our universe. And people have measured this kind of effect in white dwarf systems and other neutron star binary systems. So this is something we pretty much know is happening. So we can take this observations of systems like this in our own galaxy, and we can extrapolate to what will happen as they keep falling in. And it's pretty boring for a long time. They vary slowly. So I guess I don't have the... So the shift in the periastron time is seconds, but the actual change in the period is much smaller than that. So you have to wait for some millions of years, but eventually you'll get something once. So they were going around each other every 7 hours. Now we need them to be going around each other 100 times a second. That's cool, they'll get there eventually. And so now, well, it still looks kind of like a regular sinusoid pattern, but this is about the time when things pick up. So this is for this binary pulsar system. What happens if you just keep going? You start 2 seconds before, it's 100 times a second. It's going to actually start amping up. The amplitude of the gravitational waves increases as the system gets closer and faster together. The waves are stronger as they're kicked up. And then at the end, you actually can see them going faster and faster and at higher and higher frequency, up to a point where the equations that I'm using here break down. And you can hear this. It would sound something like this. Oh, I've unplugged the, Let's try that again. Okay. So there's a sort of a period where it's just a solid hum, and then it chirps up at the end. This is what we call the chirp signal. Okay, so that's what it would sound like for 2 neutron stars. We can also do simulations of what would happen if we had binary black holes. So this is actually one of my colleagues at California State University Fullerton, along with one of his collaborators in Canada, Harold Pfeiffer, made this movie of a binary black hole simulation where we have the curvature of space-time on the bottom and the positions of two black holes orbiting each other on the top, and then the gravitational wave produced shown at the bottom. So let me just, oops. So let me just go back again. So here, they start out far apart. The two black holes are just orbiting each other, and each orbit is almost on top of the previous orbit. So it's very similar to something you would see for normal Newtonian gravity. Then they go faster and faster, they start spiraling in more obviously. And for black holes, when they merge together, they just become a bigger black hole, and then it settles down. It sort of rings at a particular frequency right at the end of this signal here. So black holes are a little hard to hear. Here's an example slowed to quarter speed. So this is a lower pitch than the real signal would be. And you have this sort of chirp and then this sort of ring down at the end for two particular black holes. And neutron stars can also kind of do some cool stuff at the end of their orbits. So for a while, they're just sort of going around each other, and they have the regular sinusoidal sound that you've heard so far. But when the neutron stars crash together, they can actually merge into a single neutron star that lives for a while and has a high-pitched frequency that produces different kinds of gravitational waves, more like a continuous wave signal. This particular case, the merged neutron star isn't stable, and it ends up collapsing to a black hole. But again, you have something that chirps up, and then something messy happens. And if you stitch together the prediction from the mathematical model of general relativity and the prediction from the numerical simulation here, you see this sounds very similar to the one that you heard before, but it's actually a little bit different at the very, very end, the last the last 0.1 second or so, depending on the presence of matter in the neutron stars. Okay. So these are the sounds that we're listening for. There's these different chirps from different kinds of merging signals. There's the supernova make just sort of a splat sound. And then there's the continuous wave signals from spinning neutron stars, which are a pure tone. We think that the binary neutron star systems are going to be the easiest to detect with our current detectors. So let me just talk a little bit about how we plan to do that. So I'm not going to go through any technical detail at all. The general concept of how we try and detect these is we're trying to detect very, very tiny changes in relative lengths in two different directions. The way we do that is with interferometry. We take a laser, we split it to go down two paths, bounce off mirrors, come back in, and see how it interferes with itself. As the path lengths change, it's going to either cancel out or not cancel out exactly when it reaches the central point again. So this is the Gravitational Wave Observatory in Livingston, Louisiana, in the swamp. Here's the central base station. Here's some little cars parked here. Here's 4-kilometer-long arms, which have a mirror at the end of it. And these are vacuum tunnels inside the concrete housing that inside there are tunnels where we are taking a laser that's generated here, bouncing it off and back, and trying to measure across this 4-kilometer distance an effective change of distance that is smaller than the width of a proton. So it's pretty tricky, but we've been able to do this. Here's the other one in the United States is in Hanford, Washington. Since it's pretty tricky, we want to have at least 2 detectors so that we can rule out some of the artificial noise-generated wiggles of the system just from seismic activity or things like that. We're looking for things that happen the same way in multiple detectors so we can rule out some accidental noise sources. So in 2010, the initial LIGO project concluded. There's the 2 LIGOs in the US, there's also Virgo in Italy, and Geo 600 in Germany. So this was the worldwide network then. And currently, the gravitational wave community is building improved detectors. They're installing advanced LIGO and advanced Virgo in the LIGO and Virgo sites. And there's also a site being excavated in the Kamioke, I didn't spell that right, in the Kamioke mine in Japan. And a 3rd LIGO installation in India proposed. This is an example of one of the upgrades. So I mentioned seismic activity is something that could wobble our mirrors around. This is a 4-stage seismic isolation system that will try and keep the mirror isolated from any random motions that could jiggle it around and mimic a gravitational wave. So if we work out the sensitivity of these detectors, so I talked about the binary neutron stars in our galaxy are boring for kind of a long time. So we have to wait for, say, millions of years before we see the ones in our galaxy crash together spectacularly, which would be incredibly awesome and very much easier to measure on Earth than these very distant ones, but it doesn't happen often. So instead of waiting around for 1 million years, we're just going to try and listen to 1 million galaxies. So this is the basically the rough horizon of how far out we can hear binary neutron stars once advanced LIGO is completed. So the initial detectors that were running till 2010 could hear things in this little bubble at the center. The ones that we're building now can hear out to the edge of this purple bubble, and in case you can't see very well at the back, each of these dots is basically a cluster of galaxies. So this is a pretty good sampling of our local universe to hear from. And we expect about 40 mergers to happen in this volume each year. Unfortunately, we're very uncertain about exactly how many will happen. It could be less than 1, but probably like half a year, or 1 every 2 years, I suppose would be a more reasonable way to say that. Or it could be 1,000 a year. We really don't know right now because we've never been able to hear this before. So we're going to try and upgrade this. And then the other thing that I wanted to say about this is we don't actually hear equally well in all directions. So the pattern of sensitivity is actually something like this bubble. So here's where we are on Earth. And depending on what direction a sound is coming from, if this is a large distance out to the surface of this shape, that's a large distance we can hear to. But some directions we can't hear as well. So this is sort of what the picture, or what the idea of how this network works is. We have this network of microphones. They're a bit directionally sensitive, but they're stuck on the surface of the Earth and getting carried around. So we don't really have any pointing control like you would have with a telescope. So you just sit there listening and hoping that something happens inside this volume that you can hear in. So the signals that we're looking for, even with advanced LIGO, are going to be weak compared to the noise. So if this is sort of a random predicted noise level, these little wobbles in the middle are some of the sample signals that we'd expect to be able to hear. So unlike in traditional astronomy, this isn't something where you can look at a plate and see a picture. It's actually not something where we expect to just be able to listen to the stream and pick out the chirp signals from it. We have to do something a little more careful, which is called matched filtering. And so how many of you know Fourier transforms? Okay, maybe not as many as before. This is breaking up a signal into different components from different frequencies, and just completing the whole signal by how much is happening at each frequency. So we look at the signal that we expect at each frequency, and we compare it to what the detector does at each frequency, and we can weight it by how much noise there is also at each frequency. And then we just add up all the frequencies to get this quantity, which is proportional to the loudness of the signal in our detector. So if I look at this in terms of frequencies, this would be our neutron star signal. This is the amplitude at 10 hertz, the amplitude at 50 hertz, at 100 hertz, 500 hertz. At a kilohertz, it basically stops working as a signal. And then you compare it to how noisy the detector is in each frequency band. So at low frequency, this is where seismic noise actually limits our sensitivity. So here the noise is louder, the amplitude is larger in noise than in the signal. Here in the middle, the signal peaks above the noise floor of our detector, and then at the high frequencies, the detector is actually limited by the number of photons per cycle that are available. So it's called shot noise. It's how many photons of light per cycle of frequency are possible to detect. So with the initial LIGO, this is something that we couldn't have picked out from background. The signal to noise ratio is 3, but we're trying lots of different signals, lots of different times. That's not loud enough to be sure that it was a real signal. In advanced LIGO, this would be a very loud signal. So I'm going to talk a little bit about how we detect signals, because this tells us how we're going to be able to tell them apart. So what I want you to think about is a space where each dimension is one of those frequencies that I was talking about earlier. And let's just make it 2 dimensions, because that's basically what I can show on this picture. Okay. So we have signals that have different combinations of these frequencies, and we have something that's 0. It's our origin. So we have some signal produced by a system out in space. We have some noise in the detector that sort of buffets it around, and then we measure something over here. We're going to then try and figure out what we saw, or what we could have seen from the thing we measured. So we take our measured thing, consider how much noise could have pushed it around, and this gives us our sort of error bars on what that signal could have been. So we want our loudness measured to be loud enough to rule out this happening by accident when it's really no signal in lots of tries. The next thing we want to do is figure out what we saw. So how we do that is we say, okay, which waveform model gives us the loudest signal, or the best match to our measured signal? So we have these different kinds of wobbles, and they wobble in different ways, and they have different frequency dependencies. And we're going to compare our detector stream with each of these possibilities and see which one gives the loudest result. What this ends up being is we have our true signal here with some true parameter value, say like the mass of the system. We have what we measured, and we try and fit it. It ends up being the closest we can get to what we measured. But this will be pushed off from the true value by some amount, so we have some error bars here. We're going to measure something, and then based on our noise, we'll have some error bars on what we measured, right? So this is just how we're figuring out, without being able to see something, what it is that we saw. So there are a lot of parameters that can affect waveforms, and these each are things that we need to search over and that we can learn about when we detect one of these things. So the waveform, it's going to depend on the time that the system smashed together. It depends on where in space it was, the distance, how the orbit was aligned compared to the Earth. It depends on the masses of the things that are orbiting each other, and if they're spinning or not. That will also change the wave pattern. So we can learn about each of these things from a measurement of a gravitational wave. Not all of them can be measured very well. Here's an example of trying to localize where on the sky a signal came from if we have 3 detectors. So we have the 2 detectors in the US, and we have the detector over in Italy. And if we try and measure a signal and it's here in the sky, so if we have a globe of the Earth, we can just look at the sky and map everything down to what on Earth it's directly overhead. So a map of the Earth can also end up being a map of the sky. So if we say, okay, it's directly overhead Florida, well, we don't know exactly where on the sky it is. We actually have the little ellipse here that it's within. Some places on Earth, some directions we're not very sensitive to, and we end up not knowing where on the sky it is very well. So this can be a problem when we're trying to compare it with electromagnetic observations, where typically we can see where things are pretty well. Here we hear something, but we're not exactly sure where it came from. So the last bit, or the 2 last bits I wanted to talk about were, what are we going to use gravitational wave astronomy to learn about with respect to neutron stars, which are the objects that I particularly like studying. So neutron stars are where matter makes its last stand against the overwhelming force of gravity that's trying to collapse it down to a black hole. Okay. So this is, I'm at Fullerton, Cal State Fullerton, which is right here. I don't know if any of you have been to LA, but this is something that's around 10 to 15 kilometers around. And we have something that's 1 to 2 solar masses inside this area. So it's the average density of matter. If you work this out, this mass, this volume, the average density of matter in a neutron star is higher than the density of an atomic nucleus. So not any kind of material that we can think of on Earth, but the nucleus of that material, not including all the space the electrons are whizzing around in. We see them rotating 700 times per second. They have high magnetic fields. We can see them with radiation that they produce in radio and X-rays. But the question that arises when we start observing these objects and making these estimates of their size and their mass is, what on Earth can support something that's that dense against collapsing to a black hole? And it turns out that the answer, you need to pull in the part of physics that I haven't talked about, which is why this is so great, because it involves absolutely every possible area of physics, all in one thing. But that's quantum mechanics. So, okay, quantum mechanics in 2 principles. So the first part is something called the Pauli exclusion principle. And that's basically that no 2 electrons can be in the same identical state. They have to be distinct from each other in some way. That means on average, each electron in a star is combined to some fraction of the star's volume. Now the other part of quantum mechanics that we need for this is something called the Heisenberg uncertainty principle. Okay? And that tells us that a small uncertainty in position means that we have a large uncertainty in momentum. So as you compress a lot of electrons into a small volume, we get more and more uncertain about how fast they're moving. And that actually gives them something like a thermal pressure. It's not thermal, but it's a pressure just from the random motion enforced by the quantum mechanical principles. So that means that if we try and make something as cold as possible, the electrons will still be moving if they're compressed enough. And that gives us a pressure as a function of density that for low densities is limited by electron pressure. So we compress matter down. At some point, the electrons are compressed down enough that they can't be in the same state, so they are moving. So that gives us a pressure. Now, we have a limiting factor on this, that electrons can only travel up to light speed. So like everything else in a relativistic theory, there's a limit to how fast they can move. And at some point, the electrons are going to get absorbed into protons to form extra neutrons, instead of just whizzing around supporting pressure. But we can have the same argument with neutrons. It turns out that you can't put two neutrons in the same space either. So you can try and put neutrons closer and closer together, and then the degeneracy pressure from neutrons starts providing a pressure that stops you from going further. This is where you get the word neutron star. It's a star where what's supporting you from collapse is this degeneracy pressure of neutrons. So some messy stuff happens as you get denser and denser. The pressure increases. At a certain point, you have neutron pressure happening. And then at a certain point above that, what started out as protons and neutrons starts turning into more exotic, weird particles. So inside each proton and neutron are 3 quarks. And as you push them further and further together, now you have quark degeneracy pressure to worry about. So it keeps going. That's actually as far down as we go. It's just quarks at the bottom of it. But we're not quite sure how quarks interact. So this is what is uncertain about our picture of a neutron star. So I try and make a slice through a neutron star. I know that on the outer layers, I have these degenerate electrons, neutron-rich nuclei, and some neutrons floating around. As I compress it, the electrons can't go fast enough, so I have degenerate neutrons. But at the center, I don't really know what's happening. Our theories of predicting what matter does at that density break down. We have various approximations we can make, but they're not certain exactly what they imply. So this means that this pressure as a function of density may have different values. And it turns out that the pressure as a function of density gives me different relationships between the radius of a neutron star and how massive it is. So if we have a low pressure inside the core of a neutron star, the neutron star has a low radius, a small radius. If the pressure is high, it's a bigger neutron star. It's a large radius at the same mass. So we can use something about the size of a neutron star to tell us about the properties of quarks at incredibly high densities. So this comes into these orbits by the size of the tides. As the stars orbiting each other, they feel tides on each other just like the Earth and the Moon feel tides on each other. And the size of those tides is going to depend on how big the neutron stars are. So if we have a bigger neutron star, they're going to be more deformed by the tidal field of the other star. So we can actually talk about this parameter lambda. It's related to the radius. It's not exactly the radius. But we can do the same relationship where the different pressures inside the star give us a different amount of tidal deformation. I'm not sure why that's so slow. A different amount of tidal deformation. So large radius star also has lots of deformation. And we can put this into our waveform models. It turns out to give, for the large radius and large deformations, the stars merge faster. And as they get more compact, they end up spiraling around each other for a little bit longer before they smash together. And we can also continue this analytical prediction into an understanding of what happens in a numerical simulation when they merge. So we had the large neutron star, okay, so let me start these off. So before we looked at what were actually some largish neutron stars that started off orbiting each other. We can change those to smaller neutron stars, same mass but different radius. And we'll see that I started that one earlier actually. So the large neutron stars merged a little bit close to 10 or 11 milliseconds after the simulation started. But the larger neutron stars got almost to 13 or 12 and a half milliseconds. So based on the different kinds of matter inside the neutron stars, the waveform that they produce is different. Okay. So here's, compared to the noise spectrum, we have two different kinds of signals that come in. One that sounds like this, and one that sounds like this. It's not very different, but maybe you can hear that. So let me try this again. So the first one got a little higher pitch. Those were compact neutron stars, so they got to higher frequency. So the question that I spend most of my time researching is, can we hear that distance difference with LIGO? What is the difference, and can we hear it? So the answer is, well, it depends. But you can do things like say, well, what if I just use my numerical simulation data? How close does that sound have to be before I can tell two different equations of state, two different neutron stars apart? So for example, if I have this star which has a radius of about 11 kilometers, and this star which has a radius of about 12 kilometers, turns out I can hear the difference with my gravitational wave detector if they're at about 100 megaparsecs away, which is a distance where we might get one signal a year, but we might not. Or we might get 10 signals a year. It's really hard to tell at this point because we haven't heard any of them yet. A tricky thing is that if you double the distance, it gets harder to hear the difference between these signals than it was at the... So it's not just twice the error bar we get at twice the distance. We actually get a bigger error bar where we can only tell apart this 15 kilometer radius from the 11 kilometer radius star. So with this, it's something where we can start putting some limits on the size of a neutron star, and through that, the way that things behave at the core of the neutron stars, but we can't really make a precise measurement. We can do a little bit better. So this was just using the data from the numerical simulations. We can do a little bit better if we take our models from general relativity for just the orbital effects of the tidal parameter and match it on to the numerical simulations at the end. So what I mean by that is, so here's a thing that's frequency is a function of time. So this dashed line is the regular chirp that goes whoop. And here is something with the tidal piece added in, and here is something with the tidal piece and a numerical simulation. And if we can match the numerical simulation piece onto something that extends back to many, many, many seconds or milliseconds before we started the numerical simulation, we can make a more accurate measurement about what the differences between two signals are. And the really exciting thing about that is that if we were able to do this accurately, we would be able to tell these two 11 and 12 kilometer stars apart at a distance which is almost as far as advanced LIGO can see. So this would be a really exciting thing to be able to do. It would be some of our best measurements of the neutron star radius. The problem right now is that there's a lot of systematic errors that we create by uncertainties in the numerical simulation and uncertainties with how exactly to stitch these two types of signals together. So this is the current research that we're doing at Cal State Fullerton, is trying to improve our models for these signals so that we can reduce the error and get this to work in practice when the gravitational wave detectors come online in the next couple years. So here's an overview of what I've talked about in terms of the astrophysical implications. The promise of gravitational wave astronomy that I'm most interested in is this idea that we can take some properties of matter at its highest densities that determine the size of a neutron star, put that into our models of how neutron stars orbit each other and produce gravitational waves, and see what the signal will look like, so that when we measure a gravitational wave signal, we can use that result to learn about the properties of the densest matter in the universe. So that's all I have prepared. Hopefully I'll have some questions from you all, and thank you very much.
Okay, we have time for a few questions before our 5 o'clock break, so let's start with Tom.
So we're talking about detecting these very massive mergers, and you say this will give us distances up to sort of galaxy cluster size scales. What about the smaller scale? Now, if you're more sensitive, what's the smallest event you could detect, say, within the Milky Way, for example?
So so by small, like the
Less
close.
massive events, say, not neutron stars. Could you detect a white dwarf?
So the problem with white dwarfs is actually they're too big. So their frequency of orbit can't get to the high frequency thing that LIGO is sensitive to. We can see if a neutron star that's spinning has a little mountain, that will kick up some gravitational waves that we could see in the galaxy. But it's not guaranteed that any of them have mountains big enough to do that. So it's something that we look for in the gravitational wave detection methods, but right now we don't expect that to be as promising as binaries. But that's probably the most compact source that we're looking for. And supernova are similar to a single neutron star in what's the engine for gravitational waves.
Another one? Gordon.
When do you think we're going to have the first undeniable, detectable gravitational wave event?
So I don't know, because it's up to the universe. So my guess is probably, I'd say 2018.
Oh, I've been telling everyone 2015.
Well, so okay, 2015 is.
Plus or minus.
Yeah. So that's totally possible. I'm maybe being more cautious, but
Okay, I'll wait.
yeah. So we turn it on. 2015, we have like a realistic shot at seeing something. 2018 is about the time when if we haven't seen something, something is strange with our predictions.
Okay, it's 5 o'clock, let's break and let people leave, and then we'll have more questions after that. So let's thank our speakers.